In the last video, we were talking about chemical reactions and the idea of reactants in products. But I mentioned that we have to worry about something we call balancing. So the issue with this equation as written right now is, so this is the equation from the last time, is that we're not respecting the conservation of mass. So what this means is that when you go from the left to the right side, we should not lose any atoms or gain any. We should have the same amount of mass on each side. But if you look at this, for example, this CH4 has 4 hydrogen atoms, but this water only has 2 hydrogen atoms. So we need to have multiples of some of these molecules to be able to make all of this work from the left to the right side. You can't have any atoms just disappear or any atoms just appear in the products that weren't at the beginning. So for this one, I'm just going to write the answer, and then we're going to go over some examples to come up with where I got this from. So if instead of just writing those out, I include the fact that I want 2 oxygen molecules, and I think I'll make 2 water molecules, we can go through and count and see that the reactant side has the same number of atoms as the product side. So we've got carbon, we have hydrogen, and we have oxygen. So we'll do this for both sides. So on the left side, we have 1 carbon atom, we have 4 hydrogen atoms because there's a 4 right here, and then the oxygen, we have 2 oxygen molecules and each contains 2. So that's going to be 4 for our oxygen. Then on the right side, we also have CHNO. Carbon dioxide has 1 carbon atom. Our hydrogen, each water contains 2, but there are 2 of them. So we have 2 times 2, we've got 4 hydrogen atoms. Then for our oxygen, it occurs in both molecules. So we have 2 in the carbon dioxide, plus we have 2 water molecules that each contain 1. And if we do that, we'll get that we have 4 oxygen atoms there. So with this setup, 1 CH4 plus 2 oxygen makes 1 CO2 plus 2 waters. If we say that, then we're able to balance out all of the atoms here. A term that you may see used to talk about what we're doing here, and basically the rest of this chapter, is a word called stoichiometry. And this is just going to be the study, so this is going to be the study of the relationship between chemical quantities in a chemical reaction. Now, the reason I mention this is not because I expect you to be able to spit out this exact definition word for word. That's not very useful. But that you're going to see this term a fair bit if you try to look at other resources or if you ever ask for help. That you're wondering about, oh, I'm working on my stoichiometry. I'm trying to figure out how to use these chemical reactions to tell me something about how many molecules appear on both sides. Or later, things like how much mass there is. Or in future chapters, we'll start to have liquids. You'll have how much volume do you have. So stoichiometry is going to be a big category of problems and questions that are central to a lot of early chemistry assignments and even later ones too, that we're worried about how much do I have on each side. So now, I'm hoping that you can see that this left and right side are equal. But a fair question would be, Dr. Leslie, how did you know to just put a 2 in those 2 spots? So we're going to go through some steps you can use to solve these. And we're going to do it with another example. And I'm going to do it one step at a time. And then we'll have some practice for you to try. I think these are really nice questions in the sense that they work out over time. And so you start to build some intuition. Because at first it's really hard to look at one of these and solve it. And then as you get going, it gets possible on the easier problems to just see them and go, oh, I bet I put a 2 and a 2 there. But anytime you can't just see it, you'll be able to figure it out as well. So I'm going to write out a full question and then we'll talk about it. So this is what a question might look like. Note for this one, I'm going to do some practice with naming to remind us that's a thing we have to deal with. But I promise not every problem I ever do in my class will be, okay, you have to come up with all the names and transition down, because I don't want you to miss every single question if you forgot a naming rule. So we're going to write a balanced equation. If I can spell the word balanced, well, I guess we can still write it even if I can't spell it. But we're going to write a balanced equation for the reaction between, okay, we're going to use solid cobalt 3 oxide and solid carbon to produce, make sure I get all these right, solid cobalt and carbon dioxide gas. So what we want to do is we want to write a balanced equation for this big long sentence. So when you do these problems, I'm going to break them up. I think it's I use six steps. So step number 1, write the unbalanced equation if it's not given to you. So sometimes step 1, the problem starts you off with. It tells it to you. But this one we don't have an equation yet. So you've got to decipher this sentence. So let's point out some important words. So the first thing I want to note is the beginning of the statement is talking about, in this case, things that you started with. So this is part of parsing a sentence. So we know we're looking at the reaction between, which is suggesting it's stuff we're starting with. So cobalt-3 oxide and carbon, and they're both solid, the problem tells us. Then we have our word that tells us something's changing. So we have to produce. To produce is our way of saying we're going to make stuff. And it could be other words. It could be react. It could be make in the future. It's a little closer. Okay. Try to move it a little closer. This is why I say all the words. I know it's not the easiest to read always. And they tell us what we're going to make. We're going to make solid cobalt, and we're going to make carbon dioxide gas. So if I turn those into actual chemicals, cobalt-3 oxide, oxygen has to be a -2. So this has to be O with a 2- charge. And then we don't know what the charge on the cobalt is. Oh, sorry, we do. Just kidding. Cobalt +3. So to get a +3 and a -2 together, what you end up having to do is you need 2 cobalts and 3 oxygens to get you to 6 electrons. So we have cobalt, and we're going to need 2 of those. We're going to need 3 oxygens, and they told us it's solid. We're reacting with solid carbon. Carbon is not one of our diatomics. We'll just put carbon solid. It's then going to react to make our product. So our product in this case was solid cobalt, again, not a diatomic, so we'll just put CO, plus carbon dioxide gas, CO2. So that's step 1. We want to write the unbalanced equation. So step 2, so 2 is going to be write the number of atoms of each. Atoms of each. By of each, I mean of each particular atom, write how many you have. So once you get this step down, I'm actually going to go ahead and erase it because I need to write underneath these. So that's my step 2, write the number of atoms. So we have cobalt, oxygen, and carbon. And then do the same thing on the product side and keep them in the same order so they're easy to compare. So here I have 2 cobalts, I have 3 oxygens, I have 1 carbon. Over here I have 1 cobalt, I have 2 oxygens, I have 1 carbon. So on our step 2, we check if we're already done. If these numbers are the same on both sides, you're finished and the equation doesn't need any more. Now, usually when I ask a question, that's probably not going to be true, like here. We have 2, 3, 1, 1, 2, 1. That means we're not okay. Now, our step 3 is going to be choose 1 atom at a time and balance it by adding a coefficient in front of the compound containing it. Now, this is one of those examples where the words mean a lot less than just doing a few practice things. The idea is there, but it can be harder to see. So what we have to do is we have to pick one of these compounds to put a number in front of. The idea behind this is the molecules aren't going to change identity from what we've already written. So I can't change this to be cobalt COO2. I can't take away an oxygen and cobalt. I have to keep them all together the way they're written. All I can do is I can make it so there are more of them. So I can say there were 2 of these, or 5 of these, or 55 of these. Okay, you probably won't see 55 in any question in this class. But you're going to have to put a number in front of different atoms to change these numbers. So for example, if I put a 2 in front of this, I would have 4 cobalts and 6 oxygens. So when picking this, what you want to do is you want to choose atoms that only occur in one molecule on each side first. So it's easier to make changes to atoms that only occur in one molecule. Now in this case, we don't have a problem. All of them only exist in one molecule. The cobalt only exists here and here, the oxygen here and here, the carbon here and here. Some problems though, like the problem we looked at earlier with the methane and our oxygen that we were making, there was actually oxygen in both products at the end. So you want to leave those atoms that occur in multiple setups until the very last part of your problem. This is because sometimes when you choose all the others, that one will just work out in the end. Because these are all real chemical reactions, so they've only got one possible answer that's going to be the smallest ratio between them. So it is easiest to leave those atoms that occur in multiple setups till the very end. Also, when I have a problem like this and I have atoms by themselves, completely by themselves, not connected to anything, I tend to leave them till a little bit later as well, because those are the easiest ones to do by far. So let's look at this problem. Using what I just said about atoms, I'm going to do the oxygen first. That's because it only occurs on one molecule on each side, but it's the one that's going to be hardest to do, so I want to go ahead and get it away instead of trying to do this carbon or cobalt by themselves. So I have 3 oxygens on the left, and I have 2 on the right. And that number needs to become the same instead. So the lowest common multiple of these would be to get 6 oxygen atoms. So that would involve, and I'm going to use a different color for this to show the changes. We'll put a 2 in front of this to get to 6 oxygens, and a 3 in front of the CO2 to get it to 6. Now, every time I add coefficients, I need to change the numbers down here. So at 2 in front of that means I now have 4 cobalts. I now have 6 oxygens. Over on this side, I now have 6 oxygens, but I also have 3 carbons. So my oxygens are good for now. Some problems you may have to change something more than once, so it could be the oxygens are going to change again. But for now, my oxygen's good, so we're going to go to other atoms. Doesn't matter which I choose now because these are both about the same complexity. So I'm going to go with cobalt next. I have 4 on the left side, 1 on the right. So I'm going to put a 4 here, and that changes my 1 to a 4. As you'll notice, sometimes you're only going to change one molecule, sometimes you have to change 2 at the same time. And then here I have carbon here. I have 1 carbon on the left, 3 on the products. So I'm going to put a 3 in front of here, and that changes that to 3. And now I can do into that. So everything I just did, this is what I would call my step 4. I'm going to adjust each atom one at a time until I get them to match as easily as I can. Now, once I've gone through that 4th step of going back and doing this with each atom, we have to do one final check. So let me erase step 3. We'll write down steps 4 and 5. So, there we go. So, my step 4 was to continue changing coefficients until all atoms are equal. Now, the last step, number 5, is going to be make sure there is no common factor, and I'll explain what this means in just a second. Or if there is, fix it. We're going to talk about how to do that too. So what do I mean by make sure there's no common factor, and how would you fix it? What does that mean? Because fix it doesn't sound like a whole lot. Again, I'm going to erase this so we can keep writing it with this problem. So we've gotten through step 4. We've gotten all the atoms to be the same. Now, for our step 5, this answer doesn't have a common factor. So I'm going to show another way this could have turned out. Because the way you solve these is by you just keep putting coefficients in front. So you can actually end up with some slightly different answers that are still true, but aren't a completely simplified problem yet. Let's say after you put all these numbers in, this is what you got. 4 CO, cobalt, that should be a small o, cobalt, 3 oxide, plus 6 carbon solid, goes to 8 cobalt, plus 6 CO2 gas. Well, in this case, this bottom statement is true just like the top statement's true, but it's not a good answer for our balanced chemical equation. The reason for this is all these numbers in front, you'll notice, could be simplified, just like when you simplify fractions. So if I were to divide all of these by 2, if I divide all by 2, I would get the original answer I have above. CO2O3 solid plus 3 carbon solid. That's not the best, right? And see, I'm just going to try that again. 3 carbon solid goes to 4 cobalt solid plus 3 carbon dioxide gas. So what can happen is you end up with something that has a common factor you need to divide out. So you always have to check that at the end. Did I go too far with how many atoms I had in all of these? So after you check for that, then you have your answer. This is the balanced chemical equation. So what does that equation actually mean? What it means is every time I do a reaction, I'm going to need 2 atoms, or 2 molecules of cobalt-3 oxide. I'm going to need 3 carbon atoms. And if I do that reaction once, I'm going to use up 2 of these and 3 of these, and I'm going to make 4 cobalt atoms and 3 carbon dioxide molecules. Now on top of that, a way we're going to commonly use in this class to be able to do neat chemical conversions and why this gets useful is you don't commonly have just 2 atoms, right? I can't put easily on a scale measure out with a little pair of itty-bitty tweezers, 1, 2. Technically, molecular tweezers are things, and there's an idea related to that, but you're not in lab. You're not going to try to count out 2 exact molecules. Instead, you're going to mass out a fair amount. So while it's true that this is 2 molecules plus 3 atoms makes 4 atoms plus 3 molecules, a more common way to talk about it is 2 moles of cobalt-3 oxide plus 3 moles of carbon makes 4 moles of cobalt and 3 moles of carbon dioxide. So that usage of the term moles is also true, but it uses numbers that are more productive for us. We're more likely to have a mole of something than we are to have 1 atom or 1 molecule. So for that reason, you'll usually hear that terminology, but both are true statements. This is 2 molecules plus 3 atoms, or 2 moles plus 3 atoms, or 2 moles plus 3 moles. You can also think of it with numbers we don't use in chemistry a whole lot. Technically, 2 dozen cobalt-3 oxide molecules can react with 3 dozen carbon atoms to make 4 dozen cobalt atoms and 3 dozen carbon dioxide molecules. Again, we're not likely to use that terminology, but it's a true statement. Now, I have done a lot of talking, so let's write up some questions for you to try to solve, and then I will go over them. So we'll write them up top, and then I will solve them after you pause me and get through them. So, let's do some examples, because this is definitely a technique that gets easier as you go. So let's say hydrogen, and we're not going to worry about phases for this one. I don't have them written down. We won't worry about that for now. Plus chlorine makes HCl. Calcium plus water makes calcium hydroxide plus hydrogen. C3H8, I'm not going to know what that is right now, plus oxygen makes water plus CO2. What I want you to do is pause me now and try to balance these 3 questions and see what you get, and then compare it to what I get. I hope you paused now. So, assuming you did, well, even if you didn't, these statements are still true, but I prefer that you do. Let's start with the first one. H2 plus Cl2 makes HCl. Now, once you have solved these enough, those steps I showed you, it's okay to skip them if you can easily see it. So as you get better at these, it's quite possible you could look at this and just go, oh, I put a 2 in front of this, and then everything's balanced. When you get to that point, great. But before that, I'm always going to show my work on each of these. So we have 2 types of atoms, H atoms, Cl atoms. There's 2 on the left of each. On the product side, we have H and Cl. We have 1 of each. Now I can choose either to balance. First, I'm going to start with the hydrogens. Since I have 2 on the left, 1 on the right, the easiest way to get the number the same is to put a 2 in front of this. That'll double my hydrogens. But it also doubles my chlorines. And hey, it worked out conveniently that when I put the 2 there, it balanced both, and we're done. So let's take a look at something that has a few more atoms now. Let's look at our second question. So our second question, we have calcium plus water reacts to form calcium hydroxide plus hydrogen. Now, we have calcium, we have hydrogens, we have oxygens. Calciums, oxygen, hydrogen. We have 1 calcium on the reactant, 2 hydrogens, 1 oxygen. On the product side, we have 1 calcium, we have 2 times 1, we have 2 oxygens. Oh, I did not put them in the same order. Hydrogens, oxygens. So we have 2 oxygens, 2 times that, and the hydrogen occurs in 2 different molecules. So 2 times 1 gives us 2, plus the 2 from here. So we have a total of 4. So now I've got to pick an atom to balance first. Now in this case, the way I'm going to do it is, since hydrogen occurs in multiple molecules here, I'm going to pick to do oxygen first. Calcium is the easiest, it's by itself, and it's starting off balanced, so I can't change it yet. So I'm going to go with oxygen. There are 2 oxygens on the right, 1 on the left. So I'm going to put a 2 in front of the water. That gives me 2 oxygens, and 2 times hydrogen gives me 4 hydrogens. Wow, I just had to put a 2, and that made it balanced. I like pointing that out, that sometimes your balance is just going to be changing one number. And I mention that because I know, just not from being able to do it in a chemistry lab scenario, but on a test-like scenario, that freaks students out sometimes. You're like, no, it can't just be that one number. There's got to be more to do. It's okay to do that. That happens. That's not bad. And sometimes it's all 1. That'll happen too. So let's take our third example now. So we've got these 2. Let's take a look at it. So we have C3H8 plus O2 reacts to form water plus CO2. Make that look more like an 8. So we have carbons, we have hydrogens, we have oxygens. We have 3, 8, 2. And on the product side, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens when you add up both sides. So again, for this one, we want to figure out what we want to leave to the end. And I'm going to leave the oxygen to the end because it occurs in 2 different molecules on the product side. It's going to be the hardest to do. So between carbon and hydrogen, I can pick either. I'm going to start with carbon. So for carbon, I have 3 on the left, 1 on the right. So I need to put a 3 in front of my CO2, and that's going to give me 3 carbons. And 3 times 2 is 6, plus 1 is 7. It's going to give me 7 oxygens. Yes. So that'll get my carbons balanced. Now then I have my hydrogens. So here I've got 2, and on the reactant side I have 8. So I'm going to put 4 water molecules. So with that, I now have 8 hydrogens. And I have 4 times 1 is 4, plus 3 times 2 is 6. I'm going to have 10 oxygens. So now that I've done the atoms that occur in only one molecule, I'm going to do oxygen at the end. I have 10 on the right, and I have 2 on the left. So if I put a 5 in front of this oxygen, I'll now have 10. And I'll now have a balanced equation to work with. So you can see as you move on, you can get more and more questions in them, but you're able to balance them in the end, is the idea. Now, let's see. Let's look at one more example where we're going to do something like this, but where we've got to do an extra step. So I'm going to purposely work with one that has kind of big numbers, because it's good to know that it's okay for our numbers to turn out a little big. They're still manageable. So for our last example, let's take a look at, now let's just do this one's slightly smaller. We'll do it first. C4H10. Is that going to do what I want it to do? Basically, I want to make sure that something happens that makes the problem a little harder. Yeah, this one should work. C4H10 plus oxygen reacts to form CO2 plus water. You're going to see these a lot because these are something called combustion equations. So when I take hydrocarbons and I react with oxygen, I'm always going to make CO2 and water. And it's fairly important, right? It's things like how your car engine works, because gas combusts this way. You can do something like an octane combustion. So because of that, you're going to see a lot of these reactions. They're fairly relevant. Now, let's write down our amounts, CH and O. So we have, actually, yeah, I'm just going to show you this example because the next step you might not have to do. If you're confident, feel free to pause me and try it. But I'm going to show you something that's a little different. So I'm okay with us just going ahead and looking at this one. 1 carbon, 2 hydrogens, 3 oxygens. So initially it looks about the same. I'm going to start by trying to fix my carbons. I'll put a 4 in front of this. That makes 4 of these plus 8, 9 oxygens. Now I'm going to try to fix the hydrogen. I'm going to put a 5 in front of my water. That will give me 10 hydrogens, and it's going to give me 5 plus 8, 13 oxygens. So initially you're like, okay, let's just make the oxygens the same. The thing that sometimes bothers students here is, I've got a 2 and a 13. How would I make those work? So I want to get both to 26, right? So I'm going to do that by putting a 13 in front of this. And then if I want to get this to 26, I'm going to double both of these. So I'm going to make it an 8 and a 10. Now, since we changed that, I also have changed my carbons to 8 and my hydrogens to 20. Well, now they're not balanced, so let's take the carbons. It's an 8. Over here's 4. I'll put a 2 in front. That'll go to 8. That'll go to 20. So we end up with 2 C4H10 plus 13 oxygens makes 8 carbon dioxides plus 10 waters. Now, I want to point out that if you look this up, there are some other ways to do this with fractions that also work. So if you have a different way you've learned to do this, where you start by making this like 13 halves and you know how to do that, that's okay. Or if you go and watch someone else solve this, that's fine, as long as you get to this answer in the end. I like this way of doing it, but there are other ways to think through this one as well. So with that, these are definitely a type of problem I recommend making sure to get some practice on, because as you do them, I think this gets a lot easier, because it feels kind of overwhelming at first, but it takes this pattern on, and because the numbers get kind of familiar, you get used to looking like, oh, I should double this one or triple this one, and it gets to where it feels much more comfortable after you've practiced it for a while.